design. So in the power stage design, we are going to turn off the spike simulation. Okay, so I'm going to talk about basic sinusoidal control. I'm going to talk about the three-phase inverter. We'll talk about the gate driver, current feedback, inverter design, layout considerations, and then EMI filter design. Okay, so we're going to talk about the basic topologies. We're going to talk about the quarter bridge, half bridge, full bridge. We will not talk about any complex architecture at the moment. So this is your, I guess we're going to even skip the quarter bridge. We'll just straight go to the half bridge configuration. So half bridge configuration, essentially, if you have a winding here on the output, this is your battery voltage. And then what you do is, in order to simplify your analysis, you imagine you have two capacitors here, and you're able to split the voltage in half. Okay? So this becomes essentially your neutral point, and then you have two switches here, and then you can imagine your winding here. Okay, so if you have a neutral connected here, you can imagine that you have a winding connected between neutral and this point, right? So this is a simple half bridge. In a full bridge design, you essentially have four switches, and you can put, if you have your three windings and their neutral is also available, then you can actually put full available voltage across the winding. That's a full bridge design. So full bridge design also can be used when you have got all the terminals of the winding available. Normally, you only have three terminals of the winding available. So so half bridge becomes more practical use. So here, normally you have a diode, anti-parallel diode across the switches. IGBTs and MOSFETs come with it, so you don't have to do extra diodes, anti-parallel diodes in the switches. And then so let's talk about how we generate PWMs. So the PWM signal, let's talk about edge-aligned PWM, where we generate duty cycle. So you can have a reference signal and you basically generate a duty cycle. This is your ramp, right? So normally when you're generating a duty cycle, you have a period and you have an on time and off time. And this is how we convert digital information into voltage information. Okay, this is our key to convert digital information into voltage information using the inverter, using the half bridge or the full bridge. Okay, so here essentially you can generate a duty cycle. Edge aligned means you're aligned with edge when you're generating. So your period essentially starts with an edge. Okay, so you have a timer. The timer value goes up. Your timer reaches a certain value. You have positive pulse. Then you go down. So similarly, you have a timer, your new value, you go up, go down. Okay? That's how you do it in the microcontrollers or the DSPs. Now, so here is, I guess you can see here, you will get two pulses. If you have complementary PWMs on your microcontroller, you will have a high and a low. Okay. Now, and here you can also have what is called center aligned. Center aligned PWM is that you actually are evenly distributed across the center when you do a PWM signal. So here you can see how that is generated. Now your period, basically you have on cycle here, then you have an off cycle, then you have on cycle, then you have off cycle, right? So this is PWM1, this is PWM2. So the beauty of alignment when you're doing aligning, so if you look at your edge aligning, when you do edge alignment, all of your 6 switches are turning on and off at the edge. Okay, so edge aligned creates a lot of EMI, a lot of RFI, which you can avoid. Now, if you go to center aligned, so in the center aligned, now your switches are staggered. Okay, your first is here, second is here, then this is here, this is here, and the third one will have a different switching different switching instance. So you have the advantage of having less noise when you have a center aligned. Okay, so Now so here is your, what is called complementary technique, right? Where you also have to have a dead time because you have switches in series. If you turn them on at the same time, you're going to short your DC bus. So therefore, it's important that you have a dead time between them, and then you have a high and a low. So low obviously is bigger than your high because it accommodates your dead time. Okay, so these are things we have to keep in mind. Now, the dead time takes away also from the voltage. That is a time when your duty cycle does not convert into output voltage. That means that voltage is not available to the motor. So you have a net reduction in available voltage to the motor when you have a dead time. So least amount of dead time is preferable, but then you also have to keep in mind your switching. If your switching is not very fast, for example, if I'm using IGBTs for switching, I need to have at least 2.5 microsecond duty time, dead time. If I'm doing MOSFET, I may be able to get away with 1 microsecond dead time. If I'm using gallium nitride, I may be able to get away from, with 0.5 microsecond dead time. Okay, less than that time, the better it is in terms of getting more voltage available to the motor. So here is your full half bridge, three-phase inverter, where your goal is really to model these currents, A, B, C. They have to model in such a way to extract maximum performance out of your motor. Okay, how do you model them? How do you control them so that you get the maximum performance out of the motor? That's the key. And the key is obviously understanding the motor characteristics properly so that you can model these currents properly. So this is a very useful formula where how you convert your duty cycle into your voltage. Okay, normally the formula we use essentially based on the half bridge configuration where you can imagine a winding connected between half point of the DC bus, because that's where your neutral point is normally, right? And these two switches. So formula comes out to this way, where if your duty cycle is 50%, okay, if the duty cycle is 50%, you're going to get zero voltage across the motor, okay? And if your duty cycle is 1, you're going to get VDC by 2 voltage across the motor. If your duty cycle is 0, you're going to get negative voltage across the motor. Okay. Now, you can also use the same formula to figure out what is the desired duty cycle. So you can use the same knowledge. When you have a DC bus, you can actually generate a table saying what should be my desired duty cycle for a particular value on the voltage. So VM, for example, can be your reference. So now we are going to use this information to, now I have put here VA control. This should not be VA control. This can be IA control. I want to generate, now we're talking about scalar control, okay? We'll come to vector control as well. So in a scalar control, I want to generate 3 current references, okay? 3 current references I want to generate that I can use to inject into the motor. Okay, and these 3 current references need to be perfectly in phase with the back EMF. That's a goal. So that means when I generate this reference, this omega ET has to match the position of the rotor. Okay, so that's very important. And I should probably, so just make a note that these are your 3 references: IA control, IB control, IC control, and that is how you control the torque of the motor. Okay, 3 current references, and as you can see, I have added this half value here because I know that when this is 0, then my applied voltage here, when I have a duty cycle of 0, my applied voltage is 0. Sorry, when I have a duty cycle of 50%, then my applied voltage here, or the current, should be 0. That would be the goal. And this offset here, we're simply trying to replicate this part here. A duty cycle of 50%, I want 0 voltage. Right? So we're converting this information into these 3 references, right? So So when you generate these three references based on your position and based on the magnitude, right? Based on the magnitude you have, VM essentially is your magnitude. You are trying to control the value of your torque with the VM, right? So this is one variable which helps you control the value of your torque. Now, what you can do is you can now compare these references against ramp, up and down ramp. Okay. So when you compare these references against the up-down reference, the up-down ramp, now that gets converted into duty cycle information, right? So you're coding, you're simply encoding your duty cycle into, or your reference into a duty cycle. Okay, and this becomes your A top, B top, C top, PWMs, and the complementary becomes your A bottom, B bottom, C bottom. Okay, so that's how you generate your duty cycles to be able to control your inverter. Now, my computer is slow. All right. Hopefully I haven't missed any slides. Okay, so let's quickly talk about the gate drive design for MOSFETs, right? So we have to think about in terms of switching losses, drive circuit impedance, sourcing and sinking. So the goal really of a gate drive is how quickly can we turn on the MOSFET or the IGBT. So as the operating frequency of inverter increases, the MOSFET's required gate drive voltage must be driven to its final value in as short a period as possible within EMI constraints to minimize switching losses. Yes, the downside of having fast switching is that you can generate EMI, which can actually also generate noise in your circuit and can also, if you have a smaller dead time, can begin to interfere with your switching. Okay, so this is kind of a, you can say, an optimization you have to know about is if you're having issues with your gate drive. So another aspect is the drive circuit impedance. The drive circuit should act as a low impedance voltage source to enable the gate capacitance to be charged and discharged as quickly as possible. So both IGBTs and MOSFETs have a gate capacitance, and those gate capacitance need to be charged and discharged as quickly as possible to have faster transition. The one thing you don't want to do is put the MOSFET or put the IGBT in a linear zone. If you put them in a linear zone, it takes only a few microseconds to damage them. So hard switching is very much required in order to have efficient switching, in order to have less switching losses, right? So your driver also has to have good sourcing and sinking capability. It must also have the capability of sourcing and sinking high transient gate currents, possibly several amps in tens of nanoseconds, right? So it has to be really quick. Okay, so one way to have your gate drive is you can always employ a push-pull circuit. Now, push-pull circuit allows you, and this works well for a low-side MOSFET. It doesn't work well for high-side MOSFETs, but you could drive your MOSFETs with the push-pull circuit. Okay, very simple circuit. When you have a simple inverter, you can drive using a push-pull part. But normally, I prefer to use off-the-shelf drivers, which have got a very high amp capability of driving the gate. For example, this one here is a high side driver. Okay, so high side driver actually it has got both low side and high side driver, right? So you have two signals coming in from your microcontroller, input and low input and high input, all right? And this driver will issue pulses to the lower MOSFET and also issue pulses to the higher MOSFET. Now, higher MOSFET, we use a concept called Bootstrap capacitor. And the whole idea of the Bootstrap capacitor is it is going to supply the voltage to the gate drive, and the gate is going to float with the load. Okay, so this point also floats with the load. And as a result, you're still able to have positive gate signal between the gate and the source. Okay, so that's the whole idea behind the bootstrap capacitor. Now, the bootstrap capacitor is a critical part, which we're going to discuss here in a few in the upcoming slides. So what is the function of the MOSFET driver? The MOSFET driver has to faithfully apply pulses of exact voltage and time period, avoid misfiring of the MOSFET.
Sir,
Yes.
Yeah. With bootstrap strategy, we cannot, however, go to 100% duty cycle. No.
Correct. Yes, you
So,
cannot go to 100% duty cycle.
Like, is there any instance where you have like seen where we go for 100% duty cycle in motor control?
No, you cannot with the bootstrap. So that's a good point.
No, not with the bootstrap, but in terms of like motor control, is there any instance like where we are forced to go to 100% duty? So maybe we'll then not use bootstrap.
No, we so 100% duty cycle is not really possible, people.
Okay.
The reason it's not possible is because you are always going to have, 100% duty cycle means that your top
Dead band.
Sorry?
Yeah, dead band has to also be there. So
yes. That band has to be there, and then you cannot modulate your voltage with the 100% duty cycle. So you always have to have some kind of a dead band, which also helps to charge your bootstrap. But that's a good question. That's a very good question in terms of thinking about the duty cycle.
Does the bootstrap capacitor is charged when there is the dead time? I believe it is going to be charged when you have the low input, the low MOSFET on.
Yeah, that's a very good point. I think that's also a good point there, Constantino. So let's drive that. I think so. When does the bootstrap capacitor get charged, right? So let's think about that for a second here. So let me go back to the circuit here and let me share my screen again. Okay, so when we have the bootstrap capacitor, so I have got the top MOSFET here, and I have got the bottom MOSFET here, right? And then I have got a bootstrap sitting here at this point. And this bootstrap capacitor is being charged from a VDD, a resistor, and a diode to the silver source. Okay, so so this capacitor gets charged through this circuit here. Whenever you have this on, this capacitor gets charged, right? So that means you need to have this circuit. Now, what happens in the dead time? In the dead time, I guess you don't really have charging. Dead time, both of them are off.
Sorry,
so your screen is not shared.
Yes,
Oh.
that's.
Oh, all right. Can you see my screen?
Yeah.
Yeah. So this is your top MOSFET. This is your bottom MOSFET, and this is your boot capacitor. Okay? And this boot capacitor is getting charged only when the bottom MOSFET is on. So that means it's critical that the bottom MOSFET be on for this to get charged. In the dead time,
शेड्यूल आहे ते 4 दिवसाचा कोर्स ऍक्च्युअली पण एक मी सुट्टी लंच इन्क्लूड नाही
we have some noise here in the background. Sorry, can we mute? Okay, so the dead time, what happens in the dead time? So in that time, there is no charging of the boot capacitor. But the interesting part is, if you have a large enough boot capacitor, you can probably go off for several cycles before it requires a charge. That may not be practical to do, so you end up charging the boot capacitor every cycle when this MOSFET is on. Now, let's say if you have a very small capacitor and you are running at 97% duty cycle or 99% duty cycle. So you have to think about, in 1% time this guy is on, is that enough time to charge your boot capacitor? So it's important to monitor your voltage between these 2 points. Okay, so that's a very good point, Konstantinos. Thank you for bringing that up. Any questions? Is it clear? All right, let's go back to actual PowerPoint. All right, so you have, this is the charging path for the boot capacitor. And if this boot capacitor is not charged, it will not be able to drive the top MOSFET. Okay, something to keep in mind. Now, I can use that concept also to deliberately discharge the boot capacitor, whereas I can disable the top MOSFET if I don't want to enable it. That's an option you have in your hand of how to disable the top MOSFET apart from the signal. You could discharge the boot capacitor and not allow it to charge. Okay, so let's go to essentially, we talked about the bootstrap capacitor. So you have your gate to source voltage essentially becomes greater than your drain to source voltage plus your threshold voltage applied to the gate in order to turn on, right? So your bootstrap capacitor floats quite a bit higher than your bus voltage. It has to, in order to charge, in order to drive the top MOSFET. Okay, so the bootstrap capacitor is simple and low cost. Problematic when negative voltage is present at the source of the switching device. And here is the drive circuit operation. Essentially, you're going to charge, this is your charging path through the bottom MOSFET, and then you're discharging it essentially when you turn this Q on. Okay, so it gets a charge through your VB and this VS and along with your. All right, so these are some calculations. What is the correct value of a bootstrap capacitor? So if you look at what is the boot delta we need, it is given by the VDD, which is your supply voltage, not the DC bus voltage, but your control voltage, then your forward voltage drop, and then your gate to source minimum voltage required to turn it on. So this is the maximum allowable voltage drop, depends on the minimum gate drive voltage for high side switch to maintain. Okay, so the value of the bootstrap capacitor is calculated using total charge we need to inject into the gate divided by this delta V boot. And normally the total charge is the function of all of these currents times the turn on time we need plus QLS, right? So all these are the values we can obtain from the data sheet of the MOSFET. Okay, so here's an example. If you have Q total of 210 nanocoulombs and your delta V boot is 7.33 volt, then your C boot comes to about 28 nanofarad. Okay, so you're using 4 MOSFETs in parallel, so you need 4 times, it still comes to 0.1 microfarad. Normally, I will multiply that number 10 times, and I'll use 1 microfarad as my bootstrap capacitor. Okay, so I never really worry about bootstrap capacitor discharge. So the suggested values are, for example, here it says the suggested values are within the range of 100 nanofarad to 570 nanofarad, but the right value must be selected according to the application, as when the capacitor is too large, the charging time slows. Normally, I do not worry about the charging time because you are replenishing what you take away in driving the top gate. Okay, so yes, there's going to be a slow charging time when you have a bigger capacitor. And also, if your dead time is very short or your duty cycle is very small for the lower MOSFET, you can have an issue, right? So you have to keep that in mind, that your charging time and your low side time can conflict with your top side gate drive. Keep that in mind when you are doing your selection of the bootstrap capacitor. Okay, now let's spend a few minutes on the current sensors. So current sensors they can be painful because they have to be perfect. And
Rakesh sir, I have a question.
Yeah.
So I don't know if you have touched on this topic or not because I joined in very late today. So my question is, why specifically we go with a MOSFET and why not with an IGBT?
So IGBTs normally we use for high power, high voltage applications. So when I am dealing with, for example, anything at 460 volt level, 460 volt three-phase level, I want to use an IGBT, right? That is, I can have a 1200 volt IGBT who can handle, let's say, 600 amps, okay? MOSFET cannot handle it. Of course, now we have got silicon carbide devices who can handle higher voltages, who are replacing IGBTs. As their cost comes down, then you're going to have more and more prevalence of silicon carbide and gallium nitride MOSFETs. Okay, MOSFETs normally traditionally have been very, very effective in low voltage applications. In low voltage applications, they have a very low voltage drop efficiency. You can achieve up to 99%. Whereas IGBTs, if you use in low voltage applications, your efficiency is going to be lower than MOSFET, and they cannot. There's no point using IGBTs because switching losses are higher in IGBTs. So that's the trade-off between the IGBTs and MOSFETs. Did I answer your question? Okay.
Yes. Thank you.
Okay. All right. So let's spend a few minutes on the current sensors. So current sensors, there's a great article on current sensors here. I put a link down here from Electro Micro. So when we're looking at current sensors, we're looking at all these places. Okay. We're looking at the phase current of the motor. We're looking at the high side currents. We are looking at the low side currents. We are looking at summing off the currents on the high side or the low side. So these are the options we have when we talk about the current sensors. Okay. The question is, what is going to give us the best bang for the buck? And the options we have in terms of technology is we have the shunt resistors, Hall effect sensors, and current transformers, right? So we're going to see what makes most sense. So we talked about the high side, low side, and the phase current methods of measurement for the current feedback. So here is, let's talk about a high side measurement, right? So when we're doing a high side current measurement, essentially your sense resistor is connected to your voltage source, okay? And you're trying to sense. Now, high side current sensing, you have a measurement circuit here, and you're saying, okay, this is really, I need to know what the differential voltage is, V sense, and then divide that by R sense. Now, it's easy here, but when you bring it in the circuit, it's difficult, right? The reason it's difficult is because we have to somehow subtract this voltage from this voltage and then feed it to a microcontroller. So the cheapest way of doing a measurement is if you have a single resistor at the bottom of your bridge, okay? Now, the single resistor at the bottom of the bridge is noisy. It's going to be prone to noise because you're going to have a very low value for the resistor. Plus, you're going to have a lot of noise on this because it's close to ground, and you're trying to control all of your inverter through one sensor resistor, which may not be possible. Most cases, you need to have a really good layout to be able to exploit this properly. And then another option is to have 3 different shunt resistors at the lower side. Still cheaper than high side solution or a line solution. Now here, when you have these 3 resistors, now the issue is your gate drive gets affected with this as well. So you have to keep that in mind. Your gate drive return need to come here, not here. Okay, so when you're putting a signal, when you're trying to drive this IGBT, you want to make sure your gate returns here and doesn't come through your ground. So that's a very important layout consideration in your inverter design. So this is one phase current measurement IC. We have used 808207. Here you're trying to measure the winding current using this IC because it has a high common mode rejection ratio. But it's an expensive IC, costs $3 or $4 on IC, not a very cheap solution compared to the low side resistors you can use. So when you look at the measurement this is the best measurement you can have because it has no noise, it's the most accurate, and you do need a resistor here, and then this IC can pick up the differential part and can give you nice signal to be fed to the controller, right? However, this turns out to be a pretty expensive solution. So 808207, it has got, so measuring the winding current, gain up to 20, bidirectional. It has got a high PW common mode voltage, -4 to 65 volts, because that's what you need. If you look here, you are going to be injecting your DC bus voltage at this point, right? So when you have a DC bus voltage sitting here, you want to make sure this IC can reject the DC bus voltage and can give you the accurate value of this phase current here. So this is the best in terms of controls, okay? Now, let's talk about the Hall effect sensors. So Hall effect sensors, again, an expensive solution, but you can use it to sense your low side current as well as your winding current, right? So easy way of sensing current in which output can be directly fed to ADC, analog to digital converter. They are expensive. Accuracy can vary with temperature and may need more space because they can be, depending upon the size you pick, they can be voluminous in your board. Now, the current transformers is another option we have available, but the current transformers are mainly good for AC measurement. So if they have no bandwidth. Was there a question? So AC measurement only, they provide galvanic isolation, which is very nice, and they use the principle of a transformer, right? So here, if you see, this is basically you have a single turn of the current going through the current sense transformer, and then you have number of turns on the secondary side, and you're able to use this formula IP divided by N to calculate, and then you have a resistor here, RT, that gives you your output voltage, which you can feed to your microcontroller, okay? Normally, in the inverters, I do not use this. Normally, I will either use Hall effect sensors, or I will use 8207 in the low voltage application, or I will use the low side shunt resistors. Okay, those are my choices practically in order to use. In high power drives, where you're talking about few hundred kilowatts, you have to use Hall effect sensors. LEM is one brand, which has been giving me very faithful, but they have a very small bandwidth, right? So, but you don't need a high bandwidth. If you have even, 500 hertz output frequency, your bandwidth of 5 kilohertz is sufficient, because those are all sinusoidal currents. They're not any switching. They're not doing the switching in the winding current, okay? So here is a brief summary, different advantages and disadvantages of your low side current, low side sensor, high side sensor, and inline sensor. So if you look at the advantages, so if you have short to ground, then your high side can pick it up, okay? If you have short to ground, this inline sensor can pick it up as well. Short to supply, this can pick up low side, this cannot pick up, this can pick up. You don't need to worry about PWM cycle when you're sensing the load current, because you can sense at any time and store the value. Whereas when you have a low side and high side, you have to synchronize with your PWM cycle. Voltage rating, low voltage rating, which is why they have a low cost. High voltage rating, so it can have a high cost because you need to reject the low voltage. And then here is normally high because you are also putting in where you have a high voltage, access to high voltage. Okay. Bandwidth required. So here, obviously, you require much higher bandwidth because now you are trying to construct switching currents back into your winding current, right? So much higher bandwidth is required here. So if you're switching at 10 kilohertz, then I want to have a bandwidth which is at least 100 kilohertz. Here, you just need 5 kilohertz bandwidth in a particular polarity, unidirectional or bidirectional, unidirectional or bidirectional. Here you have to have bidirectional because you want to be able to also sense the current going in the negative direction. Possible configuration: 1 per half edge bridge, 1 summing, 1 per half bridge, 1 summing, and then 1 per bridge. Right? Measure low side break. Yes, if you do the low side switch, if you short the low side switch, you can measure it. Here also you can measure it when you short the low side switch for breaking. High side breaking, you can again sense it here, not here, sense it here, right? Coasting, when both of your switches are off. Take posting. Can you measure the cost? Posting. It says bidirectional only. Yes, yes. So you have diodes are carrying the current. So when the diodes are carrying the current, you're able to do bidirectional measuring here. Okay. Measures and drive. Yes, yes, yes. Magnetic solution comparison to shunt-based current sensing. Smaller solution size, and smaller solution size basic or reinforced isolation built in PWM rejection. So you can have isolation here, you can have isolation here, and here you don't need isolation, but you do have to protect from overvoltage stress. Okay, so this is kind of a summary for your three sensor schemes. Any questions so far?
For low side sensing, basically we will have to do current reconstruction. So like how much computationally it takes, means how much it loads computationally. I haven't done it that way.
Repeat that question again for me.
For this first case, if you see like low side sensing type current sensor, basically we'll have to do current reconstructions, no?
Yes.
So is that computationally burdenous on, it's easier to implement?
So it is computationally burdensome because what you end up doing is not only you have to reconstruct your phase current, you also need to implement filtering because you have significant amount of noise when you use these sensors. So you are essentially transferring your physical cost into the cost of computing your current.
Of microcontroller.
Yeah. So you need to have, I would prefer to have a DSP. I can't do that to the 8-bit microcontroller. It's going to be painful to the 8-bit micro. It can be done with an 8-bit microcontroller, but you end up spending a lot of time in coding, right? So the goal should be to spend least amount of time in coding and get a product out as quickly as possible, right? So we'll talk about that too, how to get a product as quickly as possible out in the market. All right, so here is a comparison between three technologies. Sorry, Deepak, I didn't mean to cut you short. Is there any other question regarding the sensors? Okay. All right, so in terms of comparing three technologies, shunt, Hall sensor, and CTs, obviously we don't need to use the transformer part because only AC, so we don't really consider this. Between shunt and Hall sensor, good accuracy, cost obviously is low for the shunt. Isolation, you have none here. DC offset problem, yes. And saturation, no. You have a saturation problem here. Power consumption high, power consumption low. Then we go AD/DC. Both for AC and DC, not AD/DC, AC and DC. Okay. Now let's talk about some hardware design aspects. Selection of switches, selection of drivers, selecting current feedback measurement IC, and selecting bus capacity. Okay. So inverter design, we are talking about, we need to think about voltage source impedance, bus voltage capacitance. We need to think about MOSFET IGBT placement. All of these go into when you do the layout. Gate drive selection, gate drive layout, current sensor selection, current sensor layout, right? And so once you're done with this layout, also you have to make sure it's manufacturable. So layout considerations, right? So how many people know about ground planes? So when we do a layout for motor drive, we use ground planes extensively to be able to make sure that we can eliminate as much noise as possible, and so that the burden on the microcontroller is less. Otherwise, when we have noise, we end up doing a lot of computation on the microcontroller side to be able to get the right signal to the microcontroller. So how should they be connected? We'll talk about the ground planes. And then interfacing with the digital world. How do we make sure when the knowledge is transferred from the analog world to the digital world, it is transferred with the least amount of noise? So when we do the layout, one rule we keep in mind is that we want to make sure that the current loops are very short. Okay? So identifying the current loops, how the current flows, right? So as we identify the flux loops when we do the motor design, we also need to identify the current loops when we do the inverter design. That's very critical, right? We want to keep them short and sweet. So especially gate drive loops, when we are trying to do a high voltage inverter, for example, let's say we want to do a 460 volt inverter with the bus voltage is going to go all the way up to 700 volts, it becomes more critical. And there, so your gate drive circuits have to be really tight so that you don't have dV by dt phenomena, which can then cause a lot of noise into your microcontroller or DSP. Also, you want to make sure that keep these traces very short, okay? So you have to be close to the V bus, okay? So what we normally end up doing in a low voltage drives, we are going to have a V bus plane, okay? I have a whole plane on the PCB, which is called a V bus plane. And then we are going to also use film capacitors and electric capacitors close to these IGBTs or MOSFETs so that the impedance between this point and this point is small, right? So keep these traces extremely short so that we have very small impedance between the V bus and the drain of the top IGBT. Similarly, on the bottom side, we want to have zero impedance between the source of this IGBT and the ground plane. Right? So these are the important rules. When you have a high voltage drive, you are going to end up using bus bars connecting different IGBTs. So you want to make sure your bus bar design is such that you are mounting them right on the top, and then you have a grounding bus bar right on the top of these IGBTs so that your impedance is very low. So it's called the impedance control, right? So you can think about normally you can have a plane here, you can have a plane for here, plane here, plane here. These can all be internal planes in your PCB if you're doing a low voltage drive so that your impedance is very small. Okay, so coming to current sensing. So if you're doing current sensing on the low side, then what's going to happen is you do not want to common this trace with gate drive return. Even if this is the same point, your gate drive return has to come from this point here. Okay, you want no impedance for your gate drive return, okay? So gate drive return has to come right from the source back here. You may end up running two parallel traces, one for the gate drive and one for the return of your power, but it's worth it so that the gate drive currents can remain separate, okay? Similarly here, you want to keep this trace short and sweet because this is your current sensing here, and you want to have no noise, okay? And now let's talk about the switching frequency. What should be your switching frequency? Can you have 100 kilohertz as a switching frequency in your motor?
Yeah, for very small power motor we can have.
Okay. So when you have
100, 20 so what?
Okay. So what is the advantage of having 100 kilohertz switching frequency? So now let's think about, okay, so this is an important question, and I want you to think about a few things here when you start about thinking about your switching frequency. Normally, so I'll give you, I guess, let me share my screen, whiteboard. Okay, so all right, you can see my screen?
Yes.
Okay. So what I'm going to do is I'm going to draw for you just a single leg of the half bridge, okay? And I'm going to draw for you, now you're switching this to, this is your motor inductance, and then you go back. You have your L, you have the E. So when you switch at 100 kilohertz, that means your cycle is 10 microseconds, correct? So 10 microsecond cycle, essentially, if I do 50% duty cycle, I have 5 microsecond on, for example, 50%, 5 microsecond. You also have a bus capacitance here, okay? Now, with 100 kilohertz, can I reduce this value of the capacitance?
Yes.
Okay, so yes. Okay. Can I replace this electrolytic capacitance with my film capacitors so that I don't really want to have electrolytic capacitors because electrolytic capacitors are most unreliable component in a motor drive, right? Because they have a very limited lifetime, and eventually that is what the part you have to replace. Okay, so can I get them out and I say I want to do just a film capacitor? Is that possible?
For I think low power drive it is possible.
Okay. And for high power drives?
Cost-wise, I guess film capacitor will become costlier. But if we consider reliability over cost, then we can go for it.
Okay. So also, let's say I have a resistance here in, let's say I have a 0.1, okay, and I have a resistance, let's say 2 milliohms here. Will I have an issue with the 100 kilohertz drive when I have this resistance, 2 milliohms and 0.1 milliohms?
You have to work out the impedance of the 100.1 millihenry and then 2 milliohm and then work out. But I don't think the power will have any role in capacitor type because it's related to frequency, right? If you're switching frequencies, high frequency, by virtue of the logic, you can go with the lesser value of the film capacitor. I mean, the lesser value, meaning thereby you can go for a film capacitor, right?
Right. So I think the 2 points Milind has made here. One is you are looking at the impedance of this. Second is you're looking at what is this capacitor doing, right? So what is the function of this capacitor? The function of this capacitor is to really supply you with high frequency ripple, okay? Now, when you have a DC bus, when I have got, let's say, this voltage here, okay? And if I have three-phase voltages, which are, let's say if I do 460 volt three-phase voltage, and I have electrolytic capacitor, I'm going to get a DC bus voltage, which is like this, okay? Which basically, let's say it's average about 700 volt DC, okay? Now, in a single phase points, I am basically getting a voltage like this in a single phase situation, okay? So in a three-phase, you can replace the electrolytic capacitor with film capacitors, okay? In a single phase, it's more challenging because you do not have the three-phase advantage you have with a three-phase supply, right? So single phase versus three-phase, you basically have to figure out whether your drive can tolerate this 120 hertz or 100 hertz pulsation, okay? Now, other aspect you think about is, what is your control cycle? So the control cycle is your DSP cycle or microcontroller cycle. So the control cycle doesn't have to be fast. You can have a control cycle which is distinct from PWM cycle, right? So in this control cycle, you're going to, let's say you have a control cycle which is 100 microseconds. That means you are getting your information every 10 kilohertz. It'll be nice to have a faster control cycle. If I can have 10 microsecond control cycle, then I can reduce the amount of noise. I can also have the waveforms which are better for the motor, right? So motor current ripple. So coming back to your impedance here, if I have lower value of inductance, okay, 0.1 millihenry, higher frequency is better because I want to have a very nice current waveform, okay? So when you go to lower frequency and your impedance is low, you can have more ripple in the motor and you're gonna have more torque ripple in the motor, okay? So we can have advantage where, let's say if you're using a slower processor, you have 10 kilohertz control cycle, 100 kilohertz switching cycle. But if you can maintain both to be 10 microseconds, it is wonderful. Normally what happens is this, okay? Normally your motor drives run at about anywhere from 2 kilohertz to 20 kilohertz. That's your switching frequency, okay? And your control cycle also runs from 2 kilohertz to 20 kilohertz. Normally you match it. You don't have to do it, but you match it. Okay? Now, with your gallium nitride and silicon carbide devices, and also as the motor technology is maturing, the impedance of the motor is going down, okay? Because this can become into microhenries, and you need to have higher switching frequency. The higher switching frequency is better for the motor current, But higher switching frequency is bad for the inverter because you have higher switching losses. But with gallium nitride and silicon carbide, your losses are actually going down because they are much more efficient than your existing silicon MOSFETs and silicon IGBTs, okay? So that's something you have to keep in mind when you think about the switching frequency. Any questions so far?
From design point of view, I think you can better say like low power motor versus high power motor. If we look, then is there any like inherent relation between their inductances to say power? Like I
Yeah.
have 100-watt machine and I have a 100-kilowatt machine.
Yes. So I think my experience, again, my experience is not the whole universe. So my experience, what I have experienced is that lower power motor will have higher inductance. Okay. So if I look at the power here, and if I look at the impedance of
If
the
you are sharing
motors-
your screen, we cannot see it.
Oh, you cannot see? All right. Okay. So if I have power here and motor impedance here, essentially as the power increases, you basically see fairly steep, impedance doesn't really help in transferring power, right? So your impedance can come down very quickly when your power goes up. And your switching frequency similarly also comes down, follows essentially the same curve because switching frequency, and at least today, you still have efficiency issues if you're trying to switch at higher frequency, right? So the switching frequency is, goes down. You're down to 2 kilohertz here, and you may be up to 20 kilohertz here.
But then if inductance is coming down, so switching frequency.
Yeah, switching frequency should go up, right? Inductance coming down, switching frequency should go up, and that's where you can have performance issues because this 2 kilohertz is going to cause, your current is like this, but it has got a lot of ripple.
Yes.
Right? So that is where you want to go.
Anyway, for like higher power drives, we cannot go for higher switching frequency because the switching losses will be considerably on higher sides.
Yes.
So that is also the case. We don't even go for 2 kilohertz. It's below that even.
Yes,
500 to 1.5.
Yeah. I've seen lower than 2 kilohertz as well.
Yeah, in railway drives,